Good evening and welcome to Science Gallery Bengaluru's new exhibition season, Psyche. This is our fifth exhibition season and the third one that we are in fact holding online. Today's lecture is by Carl Friston. He will speak with us about me and my Markov Blanket, Sentience, and the free energy principle. Carl Friston is a theoretical neuroscientist and expert on brain imaging. He invented statistical and neuroimaging techniques such as statistical parametric mapping, voxel-based morphometry, and dynamic causal modeling. These contributions were motivated by schizophrenia research and theoretical studies of value learning, formulated as the disconnection hypotheses of schizophrenia. Professor Friston currently works on models of functional integration in the human brain and the principles that underlie neuronal interactions. His main contribution to theoretical neurobiology is a free energy principle for action and perception. He was a 2016 recipient of the Charles Branch Award for Unparalleled Breakthroughs in Brain Research and the Glass Brain Award, a lifetime achievement award in the field of human brain mapping. He also holds honorary doctorates from the University of Zurich and Radboud University. For those of you joining us for the first time today, do remember that we have Hamlet's Live episode 5 tomorrow with a performance by Padmavati Rao at 5 p.m. And the next lecture, A Silent Crisis, Suicides Among Young People in India by Saumitra Pathare at 6:30 p.m. Remember that you can type in your questions in the Q&A box, and we would, of course, love to have your feedback too. And now, like all of us in the room and on YouTube, can't wait to hear what Professor Friston has to share with us. So over to you.
Thank you. I was just thanking you for that lovely introduction and saying it's a great pleasure to be here. Let me share my screen. Again, thank you. I'm going to try and tell you about our work in trying to understand sentience, how we make sense of the world, given that our brain is constrained within a skull and we only have access to things that are happening beyond our skull via our sensory organs. So I'm going to be talking about sentience and taking a view of sentience as inference. Inference, inferring what is there in an abductive way. So what is inference? I'm going to read inference as a form of belief updating, a belief updating process that optimize something mathematically called model evidence. So before I start telling you the stories, I'm just going to describe exactly what is model evidence. It has a very simple structure. It's simply the probability of my data, my sensations, my sensorium, my observations, those things that I see or I hear, given my model or my explanation as to how those data could have been generated. In statistics, it's also known as a marginal likelihood. So if sentience is a particular kind of inference, what sorts of things optimize model evidence and thereby evince a certain kind of belief updating and a certain kind of sentience? Now, to answer that question, I'm going to tell you two stories. The first story is a little bit dense, and I apologize for that, but it's, I think, a revealing story, and it's a story that a physicist would tell. It's a story that would bring one to an understanding of how generic systems throughout the life of physical sciences self-organize, and how in that self-organization they appear to make sense of the world beyond their boundaries. And the particular kind of boundary I'm going to be talking about is a Markov blanket. And I'm going to take you through the basic physics intuitively of what it means to possess a boundary between me and everything else. And the kinds of behavior that just having a boundary implies. And I'll try and illustrate that using simulations of a little primordial soup. Having established the sort of physics of sentience, and mechanics of sense making that must be part of self-organization in generic systems, I'm then going to tell exactly the same story, but from the point of view of a brain scientist or a neuroscientist, a psychologist, trying to understand how the brain works. It's exactly the same ideas, but using different words and a different history and a different legacy. And then if we have time, I'm going to move to an active kind of sentience, an active sensing or sense making, just showing you how in artificial intelligence research, machine learning, we understand the imperatives behind the way that we sample the world. So let me start with the physics part of this. And I'm going to start with the question posed by Schrödinger. How can the events in space and time which take place within the spatial boundary of a living organism be accounted for by physics and chemistry? Now, we're not going to answer that question, but we are going to lift this notion of a spatial boundary and note that in order to talk about anything, we have to be able to distinguish or disambiguate the states of the thing from everything else. And that implies the existence of a boundary. And I'm going to read that boundary as a statistical or a mathematical construct called a Markov blanket. Now, unless you do statistics or mathematics, it's unlikely that you'll have an intuition behind a Markov blanket. So let me just introduce technically what this construct is. Imagine there's a universe, and the universe is constituted by lots of states of an abstract sort, and I'm denoting the states here by these little blue circles. The causal structure of this particular universe is denoted by these arrows here. So this state influences this state, which influences this state. And with this graphical depiction of a causal structure in some universe, I can identify some set of states, say my states, and then the Markov blanket is defined by the parents, the children, and the parents of the children. And I can identify a set of states of a universe that now constitute my Markov blanket. So what is a Markov blanket? Well, it's effectively a statistical shield or veil that insulates me from everything else and allows someone observing me to distinguish what's going on inside my Markov blanket from everything that's going on outside the Markov blanket. Technically, it means that the internal states are conditionally independent of the external states given the blanket states. So a simple way of saying that is that everything I need to know about the universe is contained within my blanket states in terms of the implications of a Markov blanket is in time. So the present provides a Markov blanket that separates the past from the future. So everything I need to know about the future should be contained in my present state. That would include things like my memories. So I'm going to make a further move here. I'm going to divide the blanket states into two kinds, those that influence that are not influenced by the internal states, and I'm going to call those sensory states, and states, active states that influence but are not influenced by the external states. And you may be asking, why am I doing that? Well, together, the internal states and the sensory states constitute now the states that I can associate with me. This partition into sensory and active states here will make much more sense if we just take a couple of examples. Say if I was a cell biologist and I like studying cells, then we could associate all the internal states of a cell with the intracellular states, all the chemical and configuration states that the inside of a cell might have. The active states could be the actin filaments that lie underneath the surface of a cell and provide it with the motility and movement, pushing the cell surface, the sensory states, into the external milieu, the external states that reciprocate with changing the sensory states that affect things going on inside the cell. So the influences here amongst these four different kinds of states are exactly the causal influences that I described when defining the Markov blanket. And this causal structure is recapitulated in you and me. So, for example, your brain has internal states, activity of brain cells, connections between different brain cells, and that brain activity or neuronal activity then influences my active states, so my autonomic reflexes, my actuators, my muscles that cause me to move, that changes the outside world, and the outside or external states reciprocate by changing my sensory states, my vision, my interoception, and those sensory states then change my internal states. So what we're describing here is a ubiquitous kind of circular causality where the inside influences the outside through the active states and the outside influences the inside through these sensory states. And for people in cognitive science, you might recognize this as a perception action cycle, again, speaking to this circular causality. What I want you to do now is to forget about the Markov blanket for a second. We're going to do some 101 physics. And the idea is that we're going to put the Markov blanket back into play and see what special kind of physics emerges just from the existence of a Markov blanket that defines things or thingness. So this is one slide of two that has some equations in it, but I'm using these equations iconically. What I want to do is understand the physics of self-organization, where X stands for states and they have some dynamics or flows and some random fluctuations. So intuitively, imagine I placed a drop of ink in a cup of water. Now, most systems that don't have any self-organization, that don't have the opportunity to form boundaries or blankets or Markov blankets, they will disperse. So the ink molecules will be subject to random buffets and fluctuations that will disperse and dissipate the ink throughout the solvent. I would expect to see the ink disperse down concentration gradients until it occupied all the solvent that it could do. That's not the kind of system that we're interested in. We're interested in systems like you and me that have this tendency to self-organize, to gather ourselves up. And I'm illustrating that here with this sort of magical ink that does indeed gather itself up again. So it looks as if these kinds of systems have a very special kind of dynamic where they appear to flow up concentration gradients. The ink molecules are trying to gather themselves up by actually moving towards regions of the solvent that has a higher concentration. So mathematically, if we translate this concentration of ink molecules into a probability density, a probability of finding me in any particular state, we actually know exactly how to describe the evolution of the dynamics of this density. I won't take you through the details, just to say that the solution to this is informative in the sense that it does indeed describe this interesting behavior where the flow of states, my dynamics, the things that change my state of being, can be understood as effectively two kinds of movement on the gradients, and this is a gradient operator, on the probability of me being in a particular state here. Now I'll just cartoon that here. So here we have the ink molecules flowing towards the center, up concentration gradients, that's this part here, and then we have another flow at right angles that just circulates on the isocontours. And this kind of behavior is ubiquitous. In fact, nearly everything that you can imagine can be passed or understood as a composition of these two kinds of dynamics or flows or changes, ranging from fast oscillations of the kind you'd find in my heart or my nerve cells, through to movements of the heavenly bodies as the moon circulates, or the sun, as the earth circulates around the sun, or even, for example, just watching water flow down a bath hole here. So you've got the sort of the downward flow due to gravity and the circular solenoidal flow that circulates on these isocontours. So a very generic aspect of the behavior of everything. So now I asked you to forget about the Markov blanket. Now we want to ask, well, what would happen if we applied this basic physics to a Markov blanket? So here's this sort of canonical hill climbing gradient ascent equation here. And this equation also applies to all the parts of the Markov blanket, all my internal states that I'm denoting by the symbol mu here, and all my active states. So that's quite interesting, because what that means is it will look as if my internal states, say for example, my brain states, and all of my action will be trying to increase this log probability of the states, in this instance, the sensory states that I am sampling from the world. It has to be like that. It can't be any other way if I exist in virtue of having a Markov blanket. There are lots of interpretations of this fundamental gradient ascent. A normative interpretation is afforded by any explanation for behavior that can be described in terms of optimizing or maximizing some quantity. In this instance, this quantity technically is a log of the probability of me being in some sensory state. So this is a sensory state and this is me here. I've just listed a few global theories, normative theories, accounts of sentient behavior that conform to this basic construct. So for example, if I am attracted to these sensory states because they have a greater probability, they are the kind of states that are sensory states that I am likely to encounter, then these become attractive and valuable. And all of these equations are saying is that all of my perception action will look as if it's trying to maximize the value of my sensory states. And from that, we can understand things like reinforcement learning. If I was an engineer, it would be optimal control theory. If I was an economist, expected utility theory. This is interesting because the negative of this value, if I was in information theory, would be known as self-information, sometimes known as surprise or surprise. And what it means is that it looks as if, while I'm increasing my value, I'm simply trying to minimize my surprise. This is known from various perspectives as the Infmax principle, minimum redundancy, and indeed the free energy principle, which we're talking about. Technically, the average surprise is known as entropy. So what we are saying is that things that exist and self-organize are those kinds of things that resist the entropic dispersion, a tendency to disorder. And of course, that's the holy grail of things like synergetics in physics. But if I was a physiologist, it's just a statement of homeostasis. It's just that I keep my physiological sensations within viable bounds. And that those bounds just define me in terms of the kind of thing that I am. I'm going to take another perspective, another reading of this quantity, the kind of reading that a statistician would adopt, and that's this model evidence that we started with, this marginal likelihood, the probability of some sensory data, the sensory states being a particular configuration, given not me or a Markov blanket, but a model of how those data were caused. And from that, we can derive things like the Bayesian brain, predictive coding, evidence accumulation. And that's the story that I'm going to tell in the second and final half of this talk. Before I do that, though, I just want to give you an idea of the nature of the self-organization and how interesting behaviors emerge when you simulate this this fundamental gradient ascent on this value or descent on the surprisal. So what we've done here is just built in silico in a computer a little soup that comprises lots of little macromolecules all bubbling away together. And you may be asking, well, why have we done that? Well, because we've written down all the physics and all the equations of motion. We know exactly what causes what and what influences what. And what we can do is we can now start to ask, is there a little organism living inside this soup defined by its Markov blanket? And if it's there, does this little synthetic creature appear to maximize its evidence or the marginal likelihood? In other words, does it look as if it's doing an elemental form of inference about the outside of this soup beyond its Markov blanket? So it's because we've written down the equations, it's easy to identify the parents, the children, the parents, the children, given some internal states here. And indeed, there is a little creature living in the middle of this synthetic soup. Here are its internal states in blue, sort of little tail, little cilium here. The active states are lying underneath the sensory states, the surface states in magenta on the outside. And these now are the particular states, or the states of this little viral-like particle, and the external states are in cyan here. So the question now is there any link or coupling between the internal states and the outside, despite the fact that they are separated by this these blanket states, the sensory and the active states? And it's very easy to show that this is the case. So here's an example using exactly that simulation before, where we've just asked the question, is there any mixture of internal states, say some pattern of neuroactivity in my brain, that is correlated with or can predict things going on in the outside, some, say, movement in my visual field? And indeed, it's easy to find these profound correlations between internal events, stuff on the inside, and movement on the outside, the movement of these external states, these cyan dots. This is just a picture, a mathematical picture of the degree of correlation, the actual movement of this state here, for example, is in cyan, and the implicit beliefs, probabilistic Bayesian beliefs about what's happening on the outside, based purely upon what's happening on the inside, are shown in red, and these intervals here, these shaded areas, denote the uncertainty about it, because these are probabilistic beliefs. They're not definitive, very precise beliefs, but they include a certain amount of uncertainty. And indeed, if you just look at that simulation and put together all the times that there's a fast movement of this external state here, and put them on top of each other, they look very, very similar to evoked brain responses in neuroscience, in brain science, looking at the responses of the brain to things going on the outside. But if you remember before, we were talking very much about the perception action cycles as being underwritten by a circular causality, or the inside is affecting the outside, and at the same time, the outside is affecting the inside. And if I was there with you, I would be asking, well, which do you think is the best explanation here? Is the outside impressing itself via the Markov blanket on the inside, and the inside is responding very much in the way that I would evoke brain responses by presenting stimuli on the outside? Or is it the other way around? Is the inside causing the outside? Do my eye movements cause some retinal slip or changes in my sensory states? And of course, the answer, when people do give the answer, they always give the correct answer. It's both. And this phenomena, this sort of circular causality, has been famously articulated and expressed for centuries. In this instance, probably most famously by Huygens, in terms of this notion of generalized synchrony between the inside and the outside. His example was the observation that if you suspend clocks from the same beam or wall, ultimately they will come to swing or oscillate in synchrony. That is the only, if you like, solution for any loosely coupled system that is self-organizing. This is a drawing by Huygens. Here's one clock, the other clock, and here's the beam. And from our point of view, we can think of the one clock as the internal states, and the second clock having the external states, and then the beam that connects them are the blanket states, here the active and the sensory states. I like this diagram because it illustrates a complete symmetry of what's going on here. So if you subscribe to this interpretation of the dynamics that ensue from just having a blanket, a Markov blanket that defines me as a thing, and that means that I am somehow representing the outside, then you also are committed to a view that the outside is trying to learn about you at the same time, which is an interesting and possibly not unsensible notion. Anyway, so let's return to this big the question that we were asking ourselves at the beginning in terms of trying to link sentience to inference and inference to maximizing model evidence. So what sorts of systems optimize model evidence? Well, we now know any system that exists in the sense of possessing a Markov blanket. So it must be self-organizing and implicitly self-evidencing in virtue of minimizing surprise or maximizing self-information or maximizing this marginal likelihood or this model evidence. And the question naturally is now, well, am I a surprise minimizing system? Well, yes, I certainly am, and I would suggest that you are. But to substantiate that claim, I'm going to close now with a brief review of the same story from the point of view of a neuroscientist, a psychologist trying to understand how the brain works. And perhaps this story can be traced back to the students of Plato, but effectively rests upon the notion that in order to perceive, in order to be sentient, you actually have to have an active internal expression or understanding or model of what caused your sensations. So this view casts the brain as a constructive organ, an organ constructing hypotheses, explanations in an inside-out way that best account for a pattern of sensory stimuli that have been generated by the external states. So this is nicely illustrated by this 16th century oil painter famed for doing still lives, that when viewed from another perspective, give you a very different visual percept, a very different explanation for what caused this pattern of sensory inputs. So if previously you saw a bowl of fruit and now you see a face, the key point here is that you made that face. That's something that you have brought to the table that best explains this pattern of sensory input and indeed the intentions of the artist. So this idea you can find throughout psychology and indeed machine learning. I think it was best and most formally articulated by Helmholtz in the 19th century. For example, objects are always imagined as being present in the field of vision, as would have to be there in order to produce the same impression on the nervous system. And this notion is clearly very close to ideas in psychology, for example, ideas from Richard Gregory, who casts perception as hypothesis testing, that to perceive is just to commit to a particular explanation for these sensory data. And that idea has found its way into machine learning and into artificial intelligence research, particularly through the work of people like Geoffrey Hinton and Peter Diane, who introduced the notion of a Helmholtz machine, inspired by and underwriting notions of a Bayesian brain, where the Bayesian part borrows from the ideas of inference and probability theory from Thomas Bayes, and also formally the work of Richard Feynman and quantum electrodynamics, who sort of provided a calculus or a free energy formulation that allowed you to simulate this kind of belief updating or evidence maximization or inference computationally. But let's go back to Helmholtz, this notion of producing the same impression on the nervous system. So that's a nice phrase because it speaks exactly to what we were talking about before in terms of our Markov blanket, our sensory veil that separates what's going on the inside of our heads from the outside. So if this view of self-organization as an evidence maximizing, surprise minimizing dynamic is true, what that means is that we are compelled to make sense of these shadows, these impressions on our sensory veil or our sensory states that constitute the Markov blanket. We are compelled to ask, what caused that? What caused these shadows here? And you may be asking, well, how does our brain do that? Well, in a sense, we already know, because we know this fundamental dynamic, this gradient descent that any self or anything, any self-organizing thing must show. And I've just written out that sort of equation again, that flow equation again, in this instance, doing a gradient descent or going downhill, trying to minimize this free energy version of the surprise. And I've written it in two ways. Again, please don't worry about the equations. They're just here to remind me to tell the story. And the story I wanted to tell here is that this fundamental, this kind of dynamic that anything should possess now can be rewritten in a way that an engineer would understand as something called a Kalman filter, or some in neuroscience it's now being people tend to call it predictive coding. And what does that mean? Well, it just means that the rate of change of my brain states, my expectations about what cause sensations, can be split into two parts. One is a prediction based upon what I already know or believe I know. And the other one is a correction or an update based upon a prediction error. And in fact, technically, the prediction error is just the gradient of this free energy that's driving the dynamics and the flow of my internal states. So what's a prediction error? Well, imagine that we have this sensory impression on our visual blanket, and we have this expectation, mu, that it was caused by a howling dog. And if I had a generative model that could generate from this expectation or this belief the sensations that I would get if my expectation was correct, then I can generate a prediction of my sensations, compare them with the actual sensations, and then form a prediction error. It's simply the difference between the sensed input, the sensory states, and that which I predict given a generative model that can generate the sensations from my expectations. And all this equation is saying is that we're going to use this prediction error to eliminate or minimize the prediction error, or indeed the sum of prediction errors squared, weighted by their precision here. So that just means that I'm using my prediction errors to drive my expectations or hypotheses, explanations for the world, in order to minimize prediction error. I will never know what's actually causing my sensations, but that doesn't matter. As long as I can find a good enough explanation, then job done. In this instance, it was actually a cat, not a dog, causing the sensory impressions. So if that's a sufficient account of the way that our brains work, that's very good, because it means we forget about all that physics and just say that the imperative for all perception and action, active inference or active sentience or sentient behavior, is simply to minimize prediction error. And I can do that in one of two ways. I can either change my mind, change the internal brain states so that I generate better predictions that are more like the sensations. And then the ensuing prediction error can then be used to improve my perception by finding better explanations that eventually eliminate the prediction error. But there's another way that I can minimize prediction error, and that's by using my active states. What I can do is resample, I can visually palpate, I can touch the world in a different way to get some new sensations that are more like the predictions. And that will do exactly the same thing. It will reduce the prediction error. So both action and perception on this view are in exactly the same game. They're both in the service of minimizing prediction error, where we can think of prediction error effectively as just the surprise, which is just the free energy. So minimizing surprisal or surprise, minimizing free energy is the same as minimizing prediction error, which just is the same as maximizing my model evidence or my marginal likelihood, which is just inference. So all of these things are the same thing. So what would that look like in a brain? It actually provides a very apt description for a lot of known neuroanatomy and neurophysiology. I've just described that for those people who are interested in sort of the structure and the dynamics of our brains. It looks exactly like what you would predict if you had this prediction error minimizing organization. remember before, in order to produce the prediction error, we had to be able to generate a prediction. And that calls on something called a generative model. So given I know what, if I knew what caused my sensations, say, for example, if I wanted to generate some sensory samples from the center of my vision down here, I need to know what caused them. I need to know, for example, what face I was currently looking at. I would also need to know how and where I was looking at the face, the kinetics of my eye movements. And given all these causes, I can now use this hierarchical or deep generative model to generate these sensations. And now the converse, the perception, is basically, can I get back from these sensory consequences to the underlying causes and basically infer, yes, it was this face that I am currently looking at and I'm visually palpating, and that's the best explanation for what's out there. So here's the generative model, these external states generating sensory states with the random fluctuations. And then on the inside of the brain, we have exactly the same architecture that is underwrites this predictive coding version of this fundamental hill climbing, gradient descent. And on the inside, we just replace the random fluctuations with prediction errors. We have this kind of architecture, which you actually see in the real brain. So, for example, sensations come in here. They are in receipt of top-down predictions. They create a prediction error, and the prediction error is sent forward to create and revise, update expectations or beliefs to make the prediction errors smaller and therefore afford a better explanation for what's going on out there. And of course, this process is repeated hierarchically, so we can describe things at multiple levels of abstraction, just using this predictive coding like dynamic that in this instance and in this deep or hierarchical generative models unfolds or unpacks as a counter stream of descending predictions that are increasingly and continuously informed by these ascending prediction errors. I just want to give you an example of this in action, but to do that, I just have to call your attention to this, this quantity here, which is basically the precision that I predict my sensory prediction errors possess. So precision is just the reliability or the confidence that I'm affording certain sources of sensory information. The sensory information, the newsworthy information, is just the prediction error, that which I cannot explain. That's the interesting bit, and I have to weight that, and I have to predict that. So I've illustrated that here just by some of these high level expectations, having predictions of precision that weight or apply a certain gain to the prediction errors, boosting them if we think they're very informative, if we're attending to them, and not otherwise. So just to show you how powerful this sort of hierarchical inference scheme is, and getting the precision of our belief updating, our predictive coding right, I just want to ask you to play a little game with me. Imagine what caused this pattern of sensory input down here. Is it a pile of pebbles or is it a pile of coins? And you may entertain two hypotheses, and you may well favor this as the best expectation that properly accounts for this pattern of input. But if I give you another hypothesis, that this is in fact a face, you will now commit to a more plausible, more accurate hypothesis that corresponds now to a more precise belief about the causes of this input. And interestingly, even if I revert to the original sensations, now, because you now have a confident, precise belief about the causes of these sensations, you can't unsee the face, even though you may not have seen the face when I originally presented this stimulus. So just showing you how beautifully context sensitive this kind of hierarchical predictive coding, this inference scheme, this sort of deep sentience can be in terms of finding the right explanation and remembering or encoding certain confident explanations for the world. So I'm going to finish very shortly, just by turning to sort of, to my mind, one of the most challenging and interesting aspects of this kind of sentient behavior, which is effectively deciding where to look next. And you can look with everything. It doesn't have to be with vision. It could be on Google. It could be attending to different interoceptive gut feelings. It could be resolving the cocktail party problem in terms of who do I actually listen to, which news channels do I tend to. All of these are fundamental in terms of this active, the sentient behavior, this active inference in terms of how, sampling information, finding the right kinds of moves and actions that will give me the right kind of information. So what is the right kind of sensory information? So I'm going to take a principled approach to this by recoursing back to the self-organization and the imperative to maximize model evidence or minimize prediction error. So if I infer the best course of action, and in the sense that my action is also a cause of my sensations, I have to infer it, just like I have to infer external states causing sensory impressions that may produce patterns like a face. If I infer the best course of action, I necessarily have beliefs about what would happen if I did that. And that's quite interesting because I now have counterfactual beliefs about the future. So people or creatures like you and me actually have very special kinds of generative models that reach into the future, specifically the future that I caused. So if I've got posterior beliefs after I've seen some evidence about what I'm currently doing, then I must have some prior beliefs. I must have some beliefs about what are the best things that I should do. And if I'm self-evidencing, I have to believe that I'm self-evidencing actions that minimize the expected surprise prediction error free energy following an action in the future. Searches, and I'll show you, and I'll finish with an example of that. Just before I do, I will make another apology for showing you equations, but these, again, these equations have been used iconically just to illustrate some beautiful mathematical symmetry between the imperatives for minimizing prediction error or maximizing marginal likelihood or model evidence in the moment, and what those imperatives look like when it comes to choosing what to do before I've actually got those data. So just for those people who are interested in the technical aspects of this sort of free energy that stands in for, or is the mathematical description of this prediction error or surprise, can be decomposed in a number of ways. If you're in machine learning, it actually is known as an evidence lower bound, an elbow. It's something that is always bigger than the negative of this log of the evidence that we've been talking about. So minimizing that, it implicitly maximizes the evidence. But it can also be understood in terms of complexity and accuracy, or the accuracy being the how small I can make my prediction errors. But there's another part to evidence which is very, very important. And that's a complexity. How much do I have to change my mind? Mathematically, this is known as a KL divergence or an information gain. So you don't need to worry about that. But think of it as the degrees of freedom I'm using up, the cost I'm invested in or investing in providing an accurate account. And what self-evidencing means and active inference means in this context is that I'm trying to find those explanations that are as accurate but as simple as possible, just in accord with things like Occam's principle. I'm going into that in some detail because if we now just take this quantity, this free energy, and think about the corresponding decompositions of free energy in the future that I'd expect following a particular action denoted by you here, then the complexity and accuracy become risk and ambiguity. So what does that mean? Well, it means that this sort of degree to which I change my mind now plays the role of the risk of an outcome I would expect given me relative to my prior preferences, the kinds of things that I actually prefer. So it's a difference between my anticipated outcomes and my and my preferred outcomes. And the ambiguity is just the expected negative accuracy. Interestingly, this divergence and log evidence here, they unpack as something called intrinsic value, the intrinsic value of looking over there or reading this news channel, and extrinsic value. The extrinsic value is just the value we were talking about earlier on in terms of reinforcement learning and optimal control theory. This is much more interesting, though. What it scores is information gain, the expected information gain, the epistemic affordance, how much I will resolve my uncertainty if I do that. And that now can be read as, if you like, the salience of looking over there or looking over here. And we can interpret this quantity here, this intrinsic value, in terms of a salience map, a map of, if I looked over here, how much uncertainty would I resolve about the causes of my sensations? Say I had the hypothesis that my sensations, when sampled from this part of the visual field, were caused by this visual object. And there are certain parts of this sampling, or certain parts I could sample, which would resolve more uncertainty relative to others. And I can map that out using this intrinsic value and create a map of where I should look next. And indeed, human subjects do indeed look at these more salient parts. And we can simulate this. And this is now the final slide. We can simulate this and create little synthetic subjects in computers that actually show this sort of visual epistemic foraging, trying to resolve uncertainty. In this particular example, this synthetic subject, had a very simple universe. She could either be looking at an upright face, a sideways face, or an inverted face. But there's a twist here. She can only sample a very small portion of the visual field at any one time. So she has to choose very carefully where to look next. And this is where she looks. This is her salience map. These are the visual samples shown dynamically down here. And crucially, by choosing the right places, the right way of palpating the world with her sensory organs, uncertainty about what's causing her sensations is progressively reduced as she's accumulating information and assembling the best kind of explanation or hypothesis that provides an account of not only what she has seen, but what she will see if she looked over here. And that is basically a simple illustration of sentient behavior, or an inactive kind of sentience and information gathering evidence from my own models, my own beliefs about my sensed world. So that everything I've said can be summarized much more gracefully by Helmholtz. Indeed, it's summarized it here in terms of each movement we make by which we alter the appearance of objects should be thought of as an experiment designed to test whether we've understood correctly the invariant relations of the phenomena before us, that is, their existence in definite spatial relations. And with that, all that remains is for me to thank those people whose ideas I've been talking about. And of course, thank you for your attention. Thank you very much indeed.
Thank you very much, Professor Friston, for a very interesting and intriguing lecture. I'm tempted to quote from Schrödinger himself, talking about the lectures from which you started your own lecture with, and where he says, so here's where it goes. The lectures attracted an audience of about 400 who were warned that the subject matter was a difficult one and that the lectures could not be termed popular, even though the physicist's most dreaded weapon, mathematical deduction, would hardly be utilized. It's good to kind of in many ways evoke that very juncture at which Schrödinger was speaking, where the physics of life and what is life. And I think those lectures, the lectures themselves, were quite historically quite significant. And although I, in my own career, never had to deal with it, because I stayed with history of physics, but and didn't quite make that transformation or make the journey towards the other sciences. But thank you very much. So what struck me, and please do put your questions in the Q&A box. And in the meanwhile, to get us started, I by no means can I claim to have understood all of this, right? I mean, I'm a historian of science. My training doesn't necessarily prepare me to understand all of this, just like many members of our audience would have captured some bits of it. And that's what makes this, of course, lecture series very interesting, because we gain a sense of how the self-same object of scientific inquiry is approached by different disciplines, and what might we usefully, in a sense, absorb from them. So, as a layperson, pretty much, to the work that you're doing, you've broken down for us the actions of a sentient being. And when I look at sort of, for someone who's not taught to break that down for themselves or make it evident to themselves, it happens sort of naturally. And of course, we make many errors along the way then, or, we some of us train ourselves better, or are better at perception, train ourselves better, train our minds better than others, etc. Some of us have the tools, some of us, don't recognize that we have the tools, and some of us, don't. Some of us recognize and have the tools. So I just, wanted to ask you as from the outside, in a sense, most of us are not aware of this, right? Like, most of us are not aware of taking these decisions. And so what does it mean for someone like, someone from another discipline, to make sense of this? So what's at stake, and how does this help us, in a way, understand ourselves in a better way? So what's at stake, and what are the implications of what you've just told us? Could you sort of help us understand that a little?
Yes, I mean, there are two ways I could read your question. One is that, you and I, at the moment, engaging in the kind of active inference and those dynamics, are not aware of what we're doing. I think that's a very important point. And then the second question, the second way I could read that is, how would you use this kind of mechanics? How would you use this calculus of sentience in a sort of in a practical way in different disciplines? So if you don't mind, I'll try and answer both levels of the question, because I think it's important to realize that the kind of sentience I was talking about is very elemental. It's just formally, as you say, in the spirit of Schrödinger. It's just a description of some sort of fundamental maths and some fundamental processes. So it's just a way of describing belief updating of a very elemental. It doesn't it doesn't entail any awareness. So all this is about, everything I've said would apply to a virus or a thermostat effectively. So it does actually beg the deep question: how come things like you and me are aware that we are sometimes making mistakes, or that we are aware that we are perceiving, or indeed, how are we aware that we are a self? How do we, selfhood, becomes another explanation, another hypothesis, and that begs deep questions. What's the difference between a virus and, say, a vegan who has self-awareness? So all sorts of really interesting questions about different kinds of things and the depth of the implicit generative models that enable them to be more and more aware of their environment, and sometimes aware that they are actually a thing in their environment, and aware of other things in the environment, and aware that other things are aware of them in their environment. Increasingly sophisticated and deeper ways of modeling a world that starts to include other creatures like me. So that's a really important, but that's not what you're asking. What you're asking is a much probably more important, possibly more important questions. How do you make this kind of mechanics useful, and how can it be used in different disciplines? So the mechanics itself, or technically it's the principle of least action, or a method of least action. So it literally is a method that you can apply to certain systems. So you can use it to understand, as a scientist, how brains work, or how anything that has a Markov blanket works, down to a single cell, how cells self-organize, right through to, say, institutions and talk about sort of cultural niche construction or ethology. So the maths applies to any self-organizing system. So that would be an academic application of it. But you can also use it practically to build artifacts that have this elemental kind of sentience. So you can now think about applications in machine learning, in robotics, for example, in data mining, and perhaps, it's not a trivial thing to think about, because if you just think about sustainability issues, for example, if you remember, this is a bit technical, but it's an illustration of how a formal understanding of, for example, sentience in the sense of data mining, getting as much as you make the best sense of any data. How can it have implications practically in terms of, say, sustainability, and possibly even, well, not climate change, but certainly the way we use fossil fuels. So the best kind of self-evidencing is that which minimizes the complexity cost. That translates into minimum use of thermodynamic energy, which means that if you find the right way of data mining, if you've got a computer that follows these principles, what it will do is it will find the best data to resolve its uncertainty, or has the greatest information gain, as simply as possible, which means it'll be as thermodynamically as efficient as possible. And given that, say, by 2024, isn't it, that 20% of our energy consumption will be basically in data farms and computing, that becomes really quite important to understand the physics of data mining, the sentience of computers. The other, another example where it's this kind of modeling or understanding is being used is in understanding ourselves, and in particular in, say, computational psychiatry. So trying to understand, you were saying before, some of us are good at it and some of us are bad at it. That's absolutely true. Babies are usually quite bad at sort of working out what's going on, whereas people like grown-ups like you and older people like me, get very skilled. In fact, so skilled that we get inflexible. So certainly there are things and creatures that are very efficient in the way, and they have efficient in their sense making. One key thing which seems to disambiguate people with many different kinds of neurological and psychiatric disorders from neurotypical people is that thing I was illustrating with the precision, with the sort of the teal colored excuse me, predicting the reliability or the precision of things. That seems to be broken in many psychiatric and neurological conditions, so that you basically have lost the ability to attend to this or that. So I think a classic example here, the poster child of this would be autism, where you cannot attenuate the precision afforded sensory information. So you can't ignore anything. So everything is surprising, and everything deserves attention, which means that can make it sometimes very difficult to build deep, coherent generative models of your lived world or your social world. So that that would be, I think, sort of a clinical and possibly more compassionate application of this kind of mechanics, understanding the particular failures of belief updating and possibly learning in certain psychiatric conditions, understanding the failures of message passing and the processes that underwrite that belief updating, and how they are mediated in terms of neurochemistry and physiology, and how that might be remediated in terms of talking therapies or behavioral therapies that may or may not be assisted by pharmacological therapies. So there are a few sort of illustrations of how you might use this.
So I should know the answer to this question. Apologies, but I think it'll be a useful answer for our audience, our young audience anyway. What discipline did you start out in? Did you start out as a physicist?
Yeah, well, I deliberately wanted to be a mathematical psychologist, so I studied both medicine and physics. So I did physics and medical sciences.
Okay. Okay, so I have at least 3 questions that I'm going to try and summarize them, or at least say them as quickly as I can. So here's someone who wants to know, In our world of unfettered information, why do we organically and involuntarily create parallel narratives that run at dire odds with existing narratives and hence increase rather than reduce surprise?
That's an excellent question. I think this comes to or speaks to a sort of fundamental notion. So on the one hand, I'm saying that self-evidencing is minimizing surprise. And yet on the other hand, I'm saying that we try to search out sensory information that will resolve uncertainty. And part of that sort of those epistemic imperatives, that epistemic affordance, means that I will be sensation seeking and I will be novelty seeking, because it is the opportunity to resolve my surprise or my prediction errors that now acquires this affordance. So the expected free energy paradoxically means you are surprise hungry. And part of being surprise hungry, where now we're talking about surprise about things that are not things that I know, but that have not yet happened. Part of that is basically having a sufficient portfolio of hypotheses that when I go and get those data, I can narrow down onto this hypothesis or this subset of hypotheses. So this is exactly what a scientist does. She has a number of hypotheses. It could be like this, or it could be like that, or possibly like that. And then she very carefully designs her experiment to get the best kind of data that will resolve uncertainty about the three hypotheses on the table. And then the next move is to recognize, well, what's a good scientist? Well, a good scientist is somebody who is able to actually create that library of parallel hypotheses or narratives. So, and if all brains are effectively good little scientists, then it makes perfect sense that if you're a good brain and you're a good scientist, you are actually going to entertain parallel narratives. I would call them alternative hypotheses. Mm-hmm. And furthermore, I will then should be choosing my information seeking, which channel, which Wikipedia pages to go to, or trusted people who have epistemic trust. Who do I listen to? I will choose about my sort of plausible hypotheses, but of course it's a very delicate game, especially in this world of fake news and truth decay and the availability of so much information. It's getting increasingly hard to do that artfully and efficiently.
Yep. Here's another interesting question, at least I think so. What is the tipping point for achieving sentience? For instance, when we grow human brain organoids in labs, is it likely that they could achieve sentience at all, or does it require more than the brain?
Oh, that's a brilliant question. So I think the best way of answering that is just introduce the notion of vagueness as a philosopher would. So vagueness here I'm using technically in the sense that how many grains of sand do you need before it becomes a pile? And of course, it's very difficult to answer that. So I think the same kind of answer would be applied to sentience in a folk psychology sense. At some point, there will be enough grains of sand. At some point, there will be a sufficient depth of your generative model that will qualify you of having some sort of minimal sentience. I think there are certain attributes of the generative models that you can clearly identify that would be necessary to support sort of meaningful sentience in the way that you and I would talk about it. First of all, you've got to have a sufficient, you have to be able to entertain the consequences of your own action. So that means immediately you have to have generative models about the future. So we're talking about, we're not talking about thermostats anymore. We're possibly even not talking about bacteria or viruses. We're talking about possibly insects and possibly sort of other smaller, say smaller mammals that now have some capacity to model or predict what would happen if they did that. I think the next move is to become, although implicit in what would happen if I did that in my generative model, you don't necessarily need to know that I am me. I think then you have this next layer, which is, oh, it's me doing this. This is a simple explanation. I'm a thing. My mum's a thing. Oh, so this is having that insight is another level, another kind of depth in the generative model, and then you can carry on and work out, well, what would a philosopher have to have? Well, she would have to have a model of a model that knew it was a self, that knew that it was, and so on and so forth. I think it's a vague answer, but there are certain structural, formal attributes of the embodied generative models that we bring to the table to explain our worlds that would certainly have different kinds of sentience associated with them.
Okay. Sort of many thoughts about, that would it unfold in a linear way, right? Like, I mean, would I be aware of me before I become aware of me doing things, right? Or this is my sort of. But anyway, I'll keep that to myself. And there are.
Well, no, I think that's a great question, because it's I think it's the other way around, and even more interestingly, I think you become aware of your mother before you become aware that you are a person.
Yes. So I am me. In fact, is a stage. I mean, one would think comes much later to many people, and sometimes not. So no, but I understand the precision with which you speak. In fact, I hugely appreciate that. So before I add my own sort of ambiguity to it, let me move to the next question which we have, where again, I think interesting. Does the entropy of the human mind change with age, and if so, how?
These are excellent questions. Yes, I think they probably do. So what we've been talking about, or certainly what I was focusing on in the presentation, was a very fast kind of self-evidencing or inference, a kind of sense-making which you do in the moment given some information. But the same rules, the same laws, the same principle of least action also applies to the parameters of these generative models that can be read as connection strengths in the brain. And when you do inference on the parameters and the laws and the contingencies that change much more slowly than states of affairs in the moment, that's called learning. And that is something we do throughout our life. I should also add there's another level, hierarchical level of self-evidencing, which is beyond the particular structure or form of a given, the connectivity of a particular generative model, but it's a very structural form. That would be structure learning. You could read natural selection as selecting the right kind of self-evidencing brains and creatures. However, let's come back to this sort of learning in a developmental context. What are the imperatives for learning? The imperatives for learning are exactly the same as imperatives for sentient inference at a fast time scale, providing accurate explanations from my lived world that are as simple as possible. So what tends to happen as you get older is that you actively try to simplify your explanations. So you deliberately remove redundant parameters from, not deliberately, but the process of optimization read as this self-evidencing results in a removal of redundant parameters and connections in your brain. So your brain literally shrinks because it's this imperative to minimize complexity and maximize the efficiency of what's going on. The price you pay is that you're now less flexible. You become very, very accurate and wise in your field of expertise. And your field of expertise may be just your daily life and watching your favorite TV programs and restricting your life in a way that you can expertly predict and navigate, because you're in charge of the data that you gather. So you have this difference between an old person who's very wise, but also stuck in their ways and would not cope very well if you changed their world. But if you allow them to stay in their world, they are very, very efficient in terms of sense making, versus a young person who's just left home, for example, who is very versatile but not very wise, and has to make lots of mistakes to do the learning, but they can cope in lots of different situations until they get older. So it's not quite entropy, it's a relative entropy. So this complexity term is technically a relative entropy. So I think it's absolutely the case that anything at any time scale, but particularly over a neurodevelopmental time scale, that complies with this least action principle, it's the complexity part of the action. So as you minimize complexity, you will minimize that relative entropy.
Okay, fascinating. I think I'm going to take what might be the last question for this evening. I'm not entirely sure I understand the question, but I'm going to pose it to you. What can we do to increase precision of predictions in psychopathological conditions?
Again, that's a very pressing question, because, of course, first I should say, ironically, it's probably a lesser question of how do you increase precision. In fact, it's probably how do you decrease precision. I know it sounds a little bit counterintuitive, but it looks as though most psychiatric conditions are either of the kind where you've got too much precision given to the sensory input. So things like attention deficit hyperactivity or autism, certain states of psychosis, say schizophrenia, traits of schizophrenia, where you have resistance to illusions because you see everything. You can't perform good. You're paradoxically more accurate in terms of the way that you make sense of sensory data. On the other hand, there are other conditions where your prior beliefs may be held with too much precision. For example, obsessional compulsive disorder, or perhaps you might read delusions as certain beliefs that that seem impenetrable to any evidence, simply because they're held with too much precision. So the question is great, but I'm just sort of just nuancing it slightly to say, how would you relax the precision? And of course, the answer is basically everything that people try to do in a therapeutic context and beyond, in terms of, say, mindfulness training and the like. So usually the approaches to this come in two flavors. There's a non-pharmacological approaches, which basically try to skill people to get some volitional control, to mentalize their deployment of precision and attention. So that almost invariably involves training in terms of attentional set. So we're talking about meditation, mindfulness, just deploying attention in a particular way, simply so that you get used to volitionally mentalizing the deployment of precision. And then on the other hand, you have pharmacological treatments, because of precision, because it's just increasing the gain of prediction errors, or the reporting of prediction errors by certain neurons. It is quintessentially a modulatory control, and most drugs in psychiatry act upon neuromodulatory transmitter systems. So nearly every drug that you can think of, and also all the brain chemicals you will have heard of, from dopamine through to adrenaline, they all act on getting the gain right. So one is now looking at sort of a pharmacological, based on an understanding of the importance of the excitability or the gain control of neural circuits, contextualized by understanding the message passing on these neural circuits in terms of psychological constructs like attention, that are in the service of affording this inference, this message belief updating, a context sensitivity, and which, to bring my answer to closure, rests very sensitively on predicting the right precision.
Fantastic. I think the young audience that has joined us this evening and myself are grateful to you for a fascinating lecture and some really precise insights into, ourselves as sentient beings. So thank you very much for taking the time to be with us. And for those of you who've enjoyed the lecture, please be aware that we put up this lecture on our YouTube channel. So do, share it with your friends and do revisit it. If there are things that strike you as things that you might want to visit again and again. Consider signing up for our next lecture on Can Machines Come Alive by Ali Hosseini, which discusses recent advances in systems biology and applies them to the question of technological progress. Do view Schizophrenia and the Brain, which is an exhibit produced by Urvaksh Mehta and Makarand Pantoji, and consider viewing Play with Reality by Anagram, all available on our website. Of course, we look forward to your feedback, and we look forward to having you all back for the next lectures and for the program that unfolds over the next few weeks. And thank you again, Professor Friston, for your time. It was absolutely fascinating.